Hey students, Friday here. The purpose of this video is to connect what we learned about radioactive dating of rocks that we learned about at the beginning of the year with M&Ms, with other ways that Earth scientists can compare ages of rocks. We can't draw logical conclusions about what is happening with the Earth if we can't piece together how old parts of it are. Those ages point to what changes have happened. And sometimes it's important to be exact, other times it's more important to just make a comparison. And so the way that we start this journey is to compare absolute and relative dating and to understand how they're different. Let's start with absolute dating, which you've already learned about. Radioactive dating is a form of absolute dating. And so when we say absolute, we're saying that we can get nearly exact to how old something is. We learned about how measuring isotopes and understanding what fraction there is can get us a very close estimate of an actual age. I'll remind you of this image here. This image shows a rock, and the rock starts with all uranium atoms. Over time, and it depends upon how quickly an atom radioactively decays, that uranium atom will fall apart into a slightly smaller atom, in this case lead, and give off a little particle that if you watch the last video, that little particle can contribute heat to the interior of the Earth. After what we call one half-life, half of that uranium has broken apart into lead. After two half-lives, 3/4 of that uranium has broken apart into lead. And after three half-lives, 7/8 of that uranium has broken apart into lead. So in each case, a half-life is halving the amount of uranium that was present in the original sample. And by understanding the ratio of the original radioactive atom to what it decays into, we can get a very precise estimate of exactly how old a rock is. Now, the truth is we don't always have the time or the resources to date a rock exactly. And that's where relative dating comes in. What does it mean when someone is a relative of you? Well, when someone is your relative, what you're doing is you're comparing your relatives to you to see what the comparable birth origins are of you and your relative. So there is a relationship that you have between you and your siblings, you and your parents, you and your grandparents. You are relating yourself to those other people who are in your family. Relative dating is all about relating rock layers to other rock layers. Relative means to compare. And so relative dating is another technique that geologists use to understand the age of things in the Earth by comparing layers of rocks to each other and using the rules of logic to decide which would be older and which would be younger. In this case, it doesn't matter so much that we know the exact age of a rock, but we would want to know whether a rock is older than another rock to help us to imagine what has happened to those rocks. There are three rules we're going to use. We call these the laws of relative dating. And remember that in science, a law and a theory and a hypothesis are different things. In the normal way that we speak, we tend to use the word theory to mean an idea. Like you would say, oh, I have a theory about that. You're saying that you have an idea about something. We use that word very, very differently in science. When you're using the word that way in your everyday life, I have a theory about something, in science we would say that you actually have a hypothesis. A hypothesis is an idea that we have, a question that we have that we're going to collect information on to get a basic understanding of whether or not we could support that idea or maybe refine that idea to get a better understanding of what's happening in the world. A theory in science is a big deal. The theory of evolution, for example. A theory in science means that we've collected a lot of evidence for something, but we're always going to keep our minds open about collecting additional evidence to continue to refine it. Laws in science are ideas that we have collected so much evidence for, and that evidence always works out the exact same way that we feel very, very confident that what we're working with is a true representation of what exists in the world. The law of gravity. We spent some time at the beginning of the year understanding what the rules are for gravity, and our exploration of gravity from the time of Newton proposing it in the 1600s our general idea of it hasn't really changed all that much since Newton's time. Now, Einstein, as we saw in the class with our space-time model with a fabric stretched across that frame, shows how we've refined our understanding of how gravity works, but the basics of gravity haven't really changed since it was first investigated. In other words, gravity is one of our 4 fundamental forces of the universe. So when we talk about 3 big laws of relative dating, when we compare the absolute date of rocks to these relative dating rules, there has never been a case where the age of rocks has been different from what we would predict under relative dating. What are our 3 laws? The law of superposition, the law of cross-cutting, the law of original horizontality. Let's talk about each of these so that we can have a better understanding of what's going on, and they'll be supported by a diagram in each case. So, law of superposition. As we always start off with many of these things, let's break down the word. Position means where something is compared to something else. Super, well, where have we heard the word super before? Superman. Okay, so Superman, Kal-El, he came to Earth, he has all these powers, and it means that he can do things that human beings can't do. Superman. He's above in terms of his capabilities. So super means above in this case. The law of superposition basically describes the logic by which when we look at layers of rock, we can make a basic decision about how their age is compared to each other, depending upon whether they are above or below other rock layers. And to do this, we got to think back to middle school and how sedimentary rocks are formed, and have that imagination in our headspace in order to be able to understand the law of superposition. So let's take a look at comparing layer G, this tan layer, to layer N, the orange layer. The way that sedimentary rocks are formed is that tiny little pieces of rocks settle down, and when they settle down, almost always in water, the water gets into the little nooks and crannies in between the little pieces of rock. Eventually, that water might evaporate, and when it evaporates, it's creating like a glue between the little pieces of rocks. Sedimentary rocks are rocks that are made up of pieces of other rocks, and whether those pieces of rocks are very tiny, less than a millimeter, like a grain of sand or less, or whether they're huge chunks of rocks, they all have the same pattern. My apologies for the bell. They all have the same pattern of being glued together when water evaporates. So sedimentary rocks almost always form in water or mud or something that has a liquid in it, and then as that liquid goes away, it acts as a glue. Now, the only way that this happens is those little pieces of rock are being pulled by gravity towards the center of the earth. Here we are, back at that fundamental force. And gravity always pulls things to the center of the earth in a flat layer. So this layer G, notice how it's sort of filled in along this line O where the green layer C is located. This layer G, the tannish rock, is always being laid down in what will eventually become a flat layer. The line between G and N is a flat layer because of the way that gravity, when it's pulling on these little rocks, evens everything out into a flat layer. The law of superposition basically states that all sedimentary rocks, when they are formed, form these flat lines between each of the layers. So when we compare layer G to layer N, layer G had to have been laid down before layer N because layer N is on top of it. Both layers have a flat top so that we know that layer G formed as those little rocks were cemented together. And then after layer G was formed at some time later, other little pieces of rocks that make up layer N were pulled by gravity down and formed into a rock layer. So in summary, the law of superposition basically says that if a layer is on top of another layer, it is younger than that layer. It had to have been laid down after the layer that is below it. So that's using the rules of logic for the law of superposition. Anything that is on top of something else, if the layers are flat, had to have been laid down after the prior rock layer. Our next law, the law of cross-cutting. And for the law of cross-cutting, we can pay attention to either line E right here or what we would call this intrusion H. which is this pink field with the little dots all located around it. The law of cross-cutting, cross-cutting, when something cuts something, it cuts into it or breaks it into two pieces, and cross means that it's going through it crossways. Cross can look a lot of different ways. It could be a line like you see with E. It could be a huge chunk of rock intruding on other layers of rock like you see with H. So the law of cross-cutting means that something is cutting through something else. What the law of cross-cutting means is that something that cuts into something can't cut into it unless it was there in the first place. So see all these layers, A, I, K, and P? These are all layers that were laid down according to what we would expect for the law of superposition. P is on the bottom, so we know that it is older than layer K, which is on top of it. I is on top of K, so that we know that it is younger still. A is on top of I, so we know that it is younger still. But notice that both of these intrusions, line E and layer intrusion H, they all cut through all of these layers. See how A continues past line E. I continues past line E. And they're all the appropriate thickness that we would expect them to be if they were laid down as a layer originally. Oh, we'll get to the law of original horizontality shortly. So since A continues, since I continues, and we see E jutting through all of them, that means that whatever separated the two halves of layer A, the two halves of layer I, the two halves of layer K, and this part of layer P by this line E, it means that E happened after all of those layers were separated or were laid down. E was doing the separating. Another way to sum up the law of cross-cutting is you can't cut through something until it's there. Let's look at the intrusion H. See how H goes into layer K, it goes into layer I, it goes into layer A, but it doesn't go into layer F. So we know that P, K, I, A all had to have been laid down as layers before H punched through up through all of these layers. We know that layer F happened after H because F was not affected by H at all. And so the law of cross-cutting basically describes that you can't cut through something until it's there. In other words, anything that is being cut through had to have been laid down first, and then the cutting event, whether a fault in the case of E that may have been caused by an earthquake, or this intrusion that may have happened via liquid rock moving up through these layers, both of those things happen after the layers were laid down. Final law, the law of original horizontality. Let's go ahead and break down the name once again. Original refers to something that came before something else. Okay? A lot of you like to talk about OG, original gangster. Well, original gangster is something awesome that came originally. Horizontality. Horizontality refers to something being horizontal. So the law of original horizontality basically defines the rules by which something is flat or not. It also defines whenever there was perhaps some weathering and erosion that happened with a layer. I'll give you examples for each. So see how layers A, I, K, and P are all tilted compared to these upper layers that we started with in the video. Layer D is flat and horizontal. Layer N is flat and horizontal. But layers A, I, K, and P are tilted at an angle. What happened there? Well, like the law of cross-cutting, where you can't cut into something until it's there, the law of original horizontality basically says that you can't tilt something until it's there. And since gravity pulls on everything into a flat horizontal layer as it's pulling it towards the center of the Earth, we know that this tilting of all of these rock layers, since they are all tilted at the same angle, had to have happened after those rock layers were laid down. P was laid down, K was laid down, I was laid down, A was laid down, but only after that were the layers tilted. We can actually combine this with the law of cross-cutting and note that this fault at line E separated all of the layers when they were tilted, and so we know that this fault happened after the layers are tilted because the fault is also tilted, and that can't have happened until the layers were tilted. So the law of original horizontality says that layers are originally laid down horizontal, and any tilting that happens after that has to have happened after the layers were laid down. In other words, you can't tilt something that isn't there. Another dimension of the law of original horizontality is with the layer C that you see right here. See how the line separating layer C and layer G is a curvy line instead of a straight line? That's telling us a little about something that happened to layer C before layer G was laid down. If layer C was laid down, it would have originally been flat, like you see here on the left side of the layer. But we do not see a straight line separating layer C from layer G. That's a signal to us as to something that happened before layer G was laid down to layer C. See how there's an arrow pointing with the letter O to the line between C and G? What this O is reflecting is what happened to layer C before layer G got laid down. In other words, there was likely some wind action, some weathering or erosion that happened to layer C to change its shape from its original flat line into this curvy line. Then, after it curved, layer G came in and filled in the shape that was below it. So we're really combining two laws here as well, the law of original horizontality with the law of superposition. We know that layer G is younger than layer C because layer G is on top of it, the law of superposition. We also know that there was an event that happened between layer C and layer G. We're calling it O. There was a weathering or wind action event before layer G was laid down, but after layer C was laid down. Original horizontality says that C was originally horizontal, but something happened to change that horizontal shape into something else. So there's three basic laws of relative dating that scientists use to help them to compare ages of different layers if they can't get into a lab and analyze the radioactive material for a sample. Thanks for watching. Define the three laws of relative dating on the back of this sheet for plate 2. Also, here's an example of a set of rock layers. Which rock layer is older? Layer E or layer D? And I'll give you a hint on this one. You're going to use two laws to make the decision. You want to use the law of superposition and the law of cross-cutting. And so I wish you success in practicing how we use relative dating to compare the ages of rocks.